Hello everyone, my name is Kevin Hollander. I'm a consulting engineer at Augsburger Com Engineering in Phoenix, Arizona. My co-author for this talk is Dr. Tom Sugar from Arizona State University. The title of our talk is Robots Augmenting Humans and is a review of our collective past research and the challenges that still remain in the field of wearable robotics and prosthetics. Since we're not able to meet, I added our pictures to this slide as an offered substitute to be in there in person. Dr. Sugar and I have been collaborating in wearable robotics research for over 15 years. I started as a graduate student in Dr. Sugar's lab, where we initially developed many of the foundational ideas for the wearable devices presented in this talk. After I graduated, we continued our collaborative efforts in the development of university research grants and eventually our co-founding of a wearable robotics research company, Spring Active. Over the last 15 years, we have focused our research efforts towards the development of compliant actuators, powered orthoses, powered prosthetics, energy harvesting, and powered exoskeletons. We continue to collaborate on projects and are currently developing a couple of different exoskeleton devices for both logistics and medical assistance purposes. On the screen is a collection of photographs of some of these past efforts. In the first panel is an active orthosis utilizing one of our earliest actuator designs. The Active Foot Orthosis project, funded by NIH, utilized our robotic tendon actuation approach and coupled to an off-board computer controller. This early work relied on the natural step and timing dictated by the treadmill and helped us prove the validity of our actuation concepts for gait assistance. In the next panel, our group had improved upon those actuation concepts and adapted them to our first powered prosthetic project, SPARKY. The SPARKY ankle was a project funded by the U.S. Army. We had taken the earlier actuation concepts and applied them to an onboard microprocessor and controller. The base controller design was developed for simple level ground walking, but its robust nature and the use of our spring-based actuator allowed it to remain stable and used in a variety of walking tasks. As seen in the video clip, our excited subject decided to take the ankle off-road and hop up on that large rock. That was a fun day. The next panel shows the continuation of that work in a U.S. Army-funded project at Spring Active. The Ruggedized Ankle project was a culmination of our team's research, learning, and effort over several projects, from the SPARKY ankle to our collaboration with the West Point Military Academy and their Running Ankle project, as well as continued development efforts at Spring Active. The Ruggedized ankle was designed to walk, run, hike outdoors over rugged terrain, and smoothly transition between each of these conditions. As seen in the video, the subject is readily able to transition between walking and running, as well as walk backwards. As shown in the next couple of panels, we've extended our work beyond ankles and prosthetics and have applied these approaches to exoskeletons. The Joint Torque Augmentation Robot, or JTAR, was a DARPA-funded project designed to assist soldiers hiking over rugged terrain and reduce their fatigue. Our focus was the use of our compliant actuation concepts and walking controllers and apply them to both ankles and hips. Our goal was to provide significant torques to the hips and ankles during walking, yet permit unobstructed, out-of-plane motions by the user. In this design, the actuators are worn on the back and drive the joints utilizing bone cables. There is one actuator per joint supporting both sides of the hip and ankles. Each actuator was independent in actuation, sensing, and control. No information was shared between the independent controllers. In the video clip, the wearer is shown to be able to hop over a wall. The actuators were on and active during this maneuver, but did not assist in the jump. The key was that neither mechanically nor through controls did the robot interfere with the user's intended motion. In the last panel, the hip actuator is reduced in size and weight and was adapted to support efforts in a warehouse environment. The HeSA project was initially funded by DARPA and then adapted to support warehouse work. HeSA focused on providing torques to the hips with peak torques at about 20 Newton meters. Like the JTAR project, the HeSA robot was designed to reduce fatigue while walking, but not interfere with other non-walking tasks. The user is allowed to go about normal work activities and not worry about robot activation. So, what is the architecture of a wearable robot? Any robot will be able to move or actuate and will be able to sense. At its heart, it'll have a computer and a controller to help it decide what to do next. The application of a robotic device onto a person implies certain requirements. Eventually, it must be made portable. so that its power source and computer must be worn. Since it is being carried, it must also be lightweight, so that the device does not diminish any benefits it's intended to provide. And most importantly, it must be safe. Safety should be considered as the first and last priority of its design. Our personal belief is that safety should be integrated into the design at the mechanical and interface level, and not just an error check in the control code. Fundamental to our actuators is the use of compliance or springs in the design. Our early work focused on ankle gait assistance. We found that utilizing a tuned spring offered several benefits in the design. As seen in the upper left-hand image is a diagram representing our basic approach. We have a motor to provide positioning of one side of the spring, while the user or environment provides force or resistance to the opposite end. If we consider a range of possible spring stiffnesses in an actuator and apply it to a specific task like ankle gait, then we can generate a plot similar to the image in the upper right-hand corner. Considering a specific design of an actuator, we see a minimum point for required motor power result. Designing around this range of stiffness values not only minimizes motor power, but also has the effect of reducing motor weight. A 3 times savings in motor power saved us a factor of 8 times in required motor weight. Ultimately, we use springs in the designs because they are a form of highly efficient energy storage. They have a tremendously high power to weight ratio, and their compliance provides a natural and safe interface coupling to the human wearer. I mentioned that our controllers are naturally stable and robust. Over the years, we've employed many different approaches to controlling our devices. What we have found is that our best controllers have 2 very important properties. 1, they must be continuous in nature, and 2, they must be time invariant. We've never been fond of a state-based control approach because a miss in state or detection mistake can lead to problems, and in the case of walking, a potential fall. Our preference is to utilize a continuous measure like a phase plot to drive our actuation models. As seen in the plot of ankle motion, the rings of the plot loop through the gait cycle and vary in radius based upon changes in stride length, which can approximate walking speed. Invariance of time or sequence cues means that we can naturally flow from one type of gait to the next without significant lag or disruption to a motor's actuation path. Just for fun, I thought I'd show you our earliest non-intuitive controller. To prove our models for spring-based actuation, we developed a false foot device that allowed an able-bodied wearer to walk with full ankle actuation from the robot. The robot did not care what the person was doing and simply drove through a pre-programmed path. It was up to the user to get in sync with the robot. This was rather comical at times, but we found that once the metronome was provided, a person could identify and match the pace of the device. Unfortunately, for us here today, the video clip only shows the times where this method worked well. More recent work from Dr. Sugar's lab has been in exploring the phase oscillator controller. This approach is very stable and robust and has been shown to work very well for periodic motions, in particular linear bouncing type motions and hip gait. The basic concept involves the application of actuation as a function of the phase angle, shown in the plot. The omega term is simply a scaling value used to normalize the data. The forcing function of this ordinary differential equation is driven by a sine function or a combination of sine and cosine function. These sinusoidal functions naturally bound the response and ensure its stability. The sine function can be used to dynamically adjust the amplitude of the oscillations at the natural frequency, whereas the cosine function can be used to adjust the frequency. The video shows the application of the method on a bouncing pneumatic actuator and the performance of its robust response. It also shows Dr. Sugar testing one of the air leg suits he and his students had developed. The device naturally responds to his variations in speed and step frequency. Volitional control is an ongoing area of research. It can be considered an ultimate goal for any prosthetic device. When a person loses a limb, their main desire is the return of the lost function and the ability to voluntarily control the replacement limb. Researchers have attempted many different approaches to solve this problem. Each of these approaches have their own positive attributes, but they also present their own practical difficulties. There is certainly room in the field for more work in this specific area. During a project in Dr. Sugar's lab, students applied a series of FSR sensors to the inner linings of a residual limb socket. and use those sensors to drive the motion of the SPARKY actuator. You can see and hear the response of our test subject.
I got my leg back.
Wow. Can you try to hold the position as something in the middle? Oh yeah.
I really feel like I'm moving my foot. I mean, because I'm contracting that muscle and boom, I love it.
So, what are the ongoing challenges in the field? As with any development effort, we must always work to improve the durability, battery life, and responsiveness of our robots. These factors address physical concerns of any wearable system. Not previously discussed in this talk is the concept of proprioception. How can we get our devices to give the equivalent of a tactile feedback to the wearer? If we want the replacement limbs to be as real and natural as possible, we, as a group, must consider the development in this research area. And of course, volitional control. It's the ultimate goal of our robotic creations, and it's an important target for our efforts. So let us remember why we do this kind of work.
It just feels dead. You know, your limb is just dead. This, you put it on and you know, it feels alive. It feels like you have a live leg. When you get the feedback that it's a live leg, incredible. Incredible. I'm ready to go.
No.
I love it. I love it.
Yeah, I need it.
Thank you.